Okay, so hello and welcome back. So basically in this video we will continue with the basically the continuity, the concept of continuity of real functions, and so what we need to do is basically so basically in the previous videos, what we talked about was the concept of continuity of a function, and we said that, for example, suppose that you have a function like, for example, some function like this. If you have a function like this and you have basically you have a hole over here and you have a dot over here, and let me show you that this is a hole, and suppose that you have this function over here. You can see that basically if I want to draw this function from negative infinity all the way up to positive infinity, I can draw the graph of the function all the way up to here, up to this point x is equal to 0. But then at x is equal to 0, I have to lift my pen from the plane of paper, and then come over here again, come back over here, and then continue with the function. Meaning that I cannot draw the graph of the function in, and I do apologize for, there is a little bit of noise here because it's gotten a little bit hot, and I have to turn on a fan, and that makes a little bit of noise. I hope that that's not too much of disturbance. But anyway, you can probably, okay, anyway, I will basically, once I'm done with this video, I will take a look at the audio in this video and see how that turns out, and then if that's necessary, we will do something about the noise. So you can see that basically this function cannot be drawn without lifting the pen from the sheet of paper, and that means that the function is not continuous at this point. And of course here you can see that, for example, if I call this y is equal to 1, and if this point is, for example, 0, 2, that basically that you can call this function f of x is equal to, for example, f of x is equal to 1 for x not equal to 0. If x is not equal to 0, then f of x is equal to 1. Otherwise, f of x is equal to 2 if x is equal to 0, right? So that's basically this function. And you can see that if you take the limit of this function, the limit of f of x as x tends to 0 from the right, for example, you will come up with 1. If you take the limit of this function as x tends to 0 from the left, you will come up with 1. Meaning that basically the limit of f of x as x tends to 0 is equal to 1. But the problem is that at x is equal to 0, f of x is equal to f of 0 is equal to 2. Meaning that the limit of f of x as x tends to 0 is not equal to f of 0, which means that the function is not continuous at x is equal to 0. Or we could have another example, meaning that, for example, let's say that you have a function like something like this, for example. Let's say that at x is equal to 0, the value of the function, let's say that you have a function like this. Now this function would be basically f of x is equal to basically 2 for x is greater than 0, and this is equal to positive 1 for x is less than or equal to 0, right? So this is basically this function that you have over here. Now you can see that basically at x is equal to 0, you can see that at x is equal to 0, that basically that the value of f of x is equal to f of 0 is equal to 1. F of 0 is equal to 1. And the limit of f of x as x tends to 0 from the right is equal to, let's say that this is equal to y is equal to 2 and this is equal to y is equal to 1, and the limit of f of x as x tends to 0 from the right is equal to 2, and the limit of f of x as x tends to 0 from the left is equal to 1, meaning that the limit of f of x as x tends to 0 does not exist. Right? So basically in this case you can see that basically the value of the function at x is equal to 0 is equal to the left hand limit of the function. But the right hand limit of the function is not equal to the right hand limit of the left hand limit of the function, meaning that the limit of the function at x is equal to 0 does not exist. And if that is the case, then again you can see that basically I cannot draw the graph of this function in one stroke. I have to lift my pen, put it over here, and then continue with the graph of the function, which means that in this case again f is not continuous at x is equal to 0, right? So basically what this means is that in order for a function to be continuous at x is equal to c, so you can say that in order for a function to be continuous at x is equal to c basically being some number belonging to the domain of f, So in order for the function f, for example, to be continuous at x is equal to c, the following conditions have to exist. Number 1, the limit of f of x as x tends to c from the left should be equal to the limit of f of x as x tends to c from the right, which implies that basically the limit of f of x as x tends to c exists. So this limit exists. And number 2, the limit of f of x as x tends to c is equal to f of c, meaning that the value of the function at x is equal to c, that is defined as well, and then that limit is equal to the value of the function at x is equal to c, and that means that your function is continuous at x is equal to c, right? Now there is only one thing that that needs to be understood before we move any further, and that is the meaning of the limit of the function at some point, right? I suppose we have talked about that before, but not probably not properly. So I will talk about that a little bit, and then we will move on to the rest of basically the story here. Now, in the previous chapter on limits and derivatives that we talked about limits and derivatives and the whole story there. Let me check the noise over here. Okay. So now let's talk briefly about the limit of a function at some point, and then we move to basically the rest of the things here. Now, basically let's consider, for example, a function, some function like for example f of x is equal to x squared. So the function f of x is equal to x squared is basically a function like this. Now, if you have f of x is equal to x squared, what that means is that basically this is a function that goes from negative infinity all the way up to positive infinity. You can see that the value of the function at x is equal to 0, for example, is equal to 0. You know that you can see that f of 0 is equal to 0, because if I set x is equal to 0, then 0 squared is equal to 0, right? Now suppose that I had this function defined this way. Suppose that I had this function defined this way, meaning that I had basically that I had the function defined this way. Suppose that I had the function defined this way, and meaning that I had f of x is equal to x squared, x not equal to 0. Now, if in this function, if I want to know the value of f of x at x is equal to 0, meaning that if I want to find f of 0, this is not defined. Meaning that there is no way for me to even know what the value of the function would be. There is no way for me to figure out what would be the value of the function if the function was defined at x is equal to 0. Of course, I know that the function is not defined at x is equal to 0. Now, what would be the value of the function? What would be the value of the function if the function was defined at x is equal to 0, right? So in many cases, basically this is very advantageous, and specifically in the case of derivatives. I'll tell you what I mean by that. Okay, so now in order to understand why limits are necessary, I mean they are just, you just have to have them. There is no other way. Otherwise you cannot take the derivative of a function. And if you cannot take the derivative of a function, you do not know the rate of change at some exact point in the domain of a function. Meaning that, for example, if you suppose that you're dealing with this function, and then, for example, suppose that this is a position function of a ball, for example, moving in a straight line, for example, something like that. So, for example, at this point and suppose that this is time and this is position. Okay. So suppose that at this point in time you're at this position, at this point in time you're at this position, at this point in time you're at this position, and so on and so forth. Meaning that your position is changing with time. Now, of course, when position is changing, that implies that there is some velocity. So velocity means the rate of change of position with respect to time, of course, by definition. So now what that means is that what that means is that then basically you want to calculate the velocity of this ball between, for example, this point in time, call it x1, and for example this point in time, call it for example x2, right? So this is the position of the ball at point x2, which is f of x2, and this is the position of the ball at x1, which you can call basically f of x1. Now, of course, the ball goes from f of x1 to f of x2 in this time interval, which is x2 minus x1, meaning that the time interval that goes by is equal to x2 minus x1, and the change in position is equal to f of x2 minus f of x1. So of course it's easy for me to calculate the average velocity of the ball between these 2 points in time, x1 and x2, meaning that I say that basically the rate of change of position with respect to time in this case is equal to f of x2 minus f of x1 divided by x2 minus x1, right? So it's very simple, and of course that's basically that is basically the slope of this line. That is basically the slope of this line that you can draw between these 2 points. So basically f of x2 minus f of x1 divided by x2 minus x1 is the slope of this line, meaning that, for example, when you want to calculate the slope of this line, forget about the whole thing. Just imagine that you have a line over here. This point on the line is f of x2. This point is x2. This point is f of x1. This point is, and basically this is x1. Then the slope of the line is equal to basically we calculate y2 minus y1 divided by x2 minus x1. Assuming that there is some point x1 comma x2, x1 comma y1 on the line, and some point x2 comma y2 on the line. Take this one as x1 y1, take this one as x2 y2, and then you can calculate the slope of the line. Meaning that the rate of change of position with respect to time, if I assume that this is the position function of some object basically moving in a straight line, the rate of change of position with respect to time, which by the way I can call the velocity of that object, by definition is f of x2 minus f of x1 divided by x2 minus x1. So f of x2 minus f of x1 is basically some positive value, is basically this interval, this interval over here. X2 minus x1 is basically this interval over here. You're taking a ratio of this value to this value, and the more change you have in position in less time, your velocity is higher, the less basically and of course this is just a fraction. The smaller the numerator, the smaller the numerator, keeping the denominator constant, the lower would be the value of the fraction, and the other way around. So you know about fractions. So we have no problem with calculating the average change in position with respect to time. Now suppose that I want to calculate the average change of position with respect to time, now this time between this point and this point over here, and I call this, for example, x3, and I call this, for example, f of x3, And so basically I will come up with a line like this, right? And now if I calculate basically f of x3 minus f of x1, f of x3 minus f of x1, and divide that by x3 minus x1, that would be basically the average rate of change of basically position with respect to time of the same object between x1 and x3, which would be the average, which I can call basically v bar of 2, for example. I can call this, for example, v bar of 1, for example, and you can just keep going. But still, you can see that basically over here, still f of x3 minus f of x1, although I have moved a little bit closer to the point x1, still f of x3 minus f of x1 is basically this value over here, and x3 minus x1 is still this value over here. So I'm still dividing some value by some other value, which gives me which is a fraction that gives me a positive number. So the average velocity is still a positive number. The average velocity, of course, could be a negative number as well, which is not a problem in physics. Of course, in mathematics, we don't normally and usually do that, but that it could be a negative number, and mathematically, of course, you can calculate that. There is no problem with that. But now imagine that basically I want to basically get a little bit closer to x1, meaning that I get closer and closer. I make x3 closer and closer to x1. I want to know what is the average velocity between, for example, x1 and, for example, 1 second after that, or 1,000th of a second after that. I can still do that. So there is still some time that has gone by. And since time has gone by, there is some distance that the object has moved. I divide the amount of movement of the object by the amount of time that has gone by, and that would be the average velocity in that 1,000th of a second, right? But now imagine that, and these are all the average velocities between the point x1 and some time after that, right? There is still some time going by. Now, basically by definition, we have something called the instantaneous velocity, which is basically the velocity of the object exactly as at, for example, x is equal to x1, meaning that no time has gone by. And if no time has gone by, then I would be calculating basically, for example, with regard to x1, I would have basically f of x1 minus f of x1 divided by x1 minus x1, and that would be equal to 0 divided by 0. This is the instantaneous velocity of this object at x1, right? Which is of course impossible. In mathematics, this is a form which is called indeterminate, and it's just not possible for me to calculate it, at least in simple algebra, in simple arithmetic. So, and now this is basically where the concept of a limit comes into play, and there it basically helps you to resolve this issue of 0 divided by 0. So how it works is that basically that's the same thing as saying that I want to calculate f of 0, for example, in the case of this function over here. You can see that in the case of this function, f of 0 is not defined. I cannot calculate it. It's just not possible. the function does not give me a value for f of 0, right? So what I want to know is that, for example, in the case of this function, I want to know what would be the value of the function if basically if f was defined for x is equal to 0. If that was the case, meaning that if f was defined at x is equal to 0, what value would it give me if I entered 0 into the function, right? And there is a procedure for that. Now the procedure for this is that so for example, as you can see, this function over here, of course, is something that it's just not defined, meaning that I'm taking the out some value, I'm subtracting the same value from that, and I'm dividing that by again some value, and I'm subtracting the same value from that. So it's just not possible for me to calculate that, right? Now what I can do is that basically in the case of this function over here, I can do a simple thing, meaning that I can draw the function. Let me draw the function over here to have some space to work with here, and so let's say that you have the function this way, and this is where the function is not defined, and this is f of x is equal to x squared, and x is not equal to 0. This is your y-axis, and this is your x-axis. So now what happens here is that I want to know what would be the value of the function if x was defined at x is equal to 0. In other words, what would be the value of f of 0 if x was actually defined at x is at 0, right? So I can do a very simple, you can call it trick. You can actually call it the trick, because mathematicians, I mean, it took really mathematicians and physicists and the whole, I mean, it took everybody like 2,000 years to come up with this simple solution. Although mathematicians are by nature a little bit skeptical, so maybe this has at some point in time somebody has actually thought about this solution, but they have never actually gone ahead with it and applied it. Although the problem is that by even by the year 1600s, 1700s, I suppose, I'm not really sure about this, but I suppose that the concept of the function was not still basically not developed, fully developed. So what we know today about these functions, that this is the input, this is the output, this is f, this is g, this is 1, this is many 1, this is unto, this is, and so on and so forth. Most probably they didn't even know about all. I mean, these things were not really still yet not a parts of mathematics. So now what you can do is that you can basically get closer and closer to 0 from the right? Meaning that I can write basically over here, I can basically examine the outputs of this function for inputs very close to x is equal to 0. Suppose that, for example, here x is equal to 0, and I'm getting closer and closer to 0 from the right, meaning that I'm inputting all of these values as 0.1, 0.01, and 0.001, and 0.0001, right? So I'm inputting all of these inputs into this function, and we're getting closer and closer to x is equal to 0. So if I do so, basically what I will get is that, for example, you know that, of course, that I don't need a calculator for this. So you know that basically 0.1 raised to the second power is equal to basically 0.01. 0.001 raised to the second power is equal to 0.0001. 0.001 raised to the second power is equal to 0. They have 6 decimal places, so 1, 2, 3, 4, 5, and 1 over here. And this number you would get 8 decimal places, so you get 1, 2, 3, 4, 5, 6, 7, and 1. So as you can see, and if I call this x and if I call this f of x, you can see that as x is getting closer and closer to 0, meaning that as you're getting closer and closer to x is equal to 0 here, the value of f of x is getting closer and closer to 0, right? It's getting closer and closer to 0, meaning that over here the value of f of x is 0.01, then it becomes 0.0001, then it becomes 0.601, then it becomes 701, and so on and so forth. So that means that as I'm getting closer and closer to 0 from the right, the value of f of x is getting closer and closer to 0, right? And I can do the same thing from the right as well, meaning that I can get closer and closer to 0 from the left. I can get closer and closer to 0 from the left and see what is the values of f of x as I do so. Meaning that I can write 0.1, 0.01, 0.001, and 0.0001, and still I will get the same values, because this is, and of course these are supposed to be negative numbers, and still I will get the same outputs, because this is f of x is equal to x squared. You'll always get positive outputs, meaning that over here you will get 0.01, and over here you get 0.001, and over here you get 0.000, so 5 zeros and 1, and over here you'll get 0 point, and you get 8, 0, 1, 2, 3, 4, 5, 6, 7, and 1. So as you can see, again, as I'm getting closer and closer to 0 from the left, the values of f of x are getting closer and closer to 0, right? So now I can say that based on this situation, I can write this idea, I can write it down as the limit of f of x as x tends to 0 from the left is equal to 0, right? And then I can also say that the limit of f of x as x tends to 0 from the right is also equal to 0. And so since both of these values are equal to 0, therefore I can say that the limit of f of x as x tends to 0, and not from the right or from the left, both of them have the same values. So now I can say that the limit of f of x as x tends to 0 is equal to 0. Which means that if the function was defined at x is equal to 0, the value of the function at x is equal to 0 would be 0, but it's not 0 because the function is not defined at x is equal to 0, right? So that is basically the whole story behind a limit. And then in the previous chapter, in class 11, we basically found some algebraic ways of finding the limits of these functions. Like, for example, we found the limits of polynomials and rational functions and trigonometric functions and so on and so forth, that we can use, meaning that you don't have to basically use this procedure over and over again. You can simply use those rules of taking limits in order to find the limit of any function, almost any function. I mean, the functions that we have talked about over there, without going through all of this business of getting closer and closer and closer to to the value of the x in the function. So that's basically the whole story of a limit. Now, so it took us about 2,500 years to come up with this simple thing. 2,500 years. It started with Zeno and Aristotle and all of those very famous people, and then kind of concluded with Sir Isaac Newton, and then after that still it took another 100 years for mathematicians to understand the idea of limits and so on and so forth. So it took about 2,000 years, let's say, for us to understand this very simple thing. Okay. So now we can assume that we know how to solve this problem as well, meaning that basically the problem of dividing 0 by 0 in this particular case, we can solve that problem as well, meaning that I know that basically this function gives me 0 by 0, but then what I can do, I can basically do the same thing, meaning that I can say that basically I keep my x1 over here, and then I get closer and closer to x1 from the right. I get closer and closer to x1 from the left and see the values of the function exactly at that point. And if I do so, I will come up with a line called not any of these lines, but called some line called the tangent line, which touches the graph of this function exactly at one point. This line over here, let me draw it using some other color that you can appreciate. I will come up with a line exactly at this point that touches the graph of the function exactly at one point, and this line would be called a tangent line, right? This line is called a tangent line. And this tangent line then would be the rate of change of basically position with respect to time, but then this time it's not average velocity, it is instantaneous velocity, meaning that it is the average velocity between x1 and x1 itself, which is, of course, logically it doesn't seem to be possible, but you can actually, using limits and derivatives, essentially using limits, because the derivative is nothing but the limit. Using the idea of a limit, you can actually calculate the average velocity of this object moving down a straight road, for example, exactly between x1 and x1 itself, and that's basically. And so then we call this basically we call this whole idea the derivative of this function at x is equal to 1, and we write it as basically the v prime, or basically you can call it whatever you want to call it, but you can call it v, which is the rate of change exactly at this point. You can call it the limit of basically f of, for example, x plus h minus f of x. Suppose that I take this as x, this point I take that as x, for example. F of x plus h, and h, you can imagine that h is some very tiny distance away from x. So f of x plus h minus f of x divided by x plus h minus x as basically as x plus h tends to x, which is the same thing as the limit of basically f of x plus h minus f of x and this becomes basically, this becomes h, and this becomes as h tends to 0. And this is basically the derivative of the derivative of f of x, and we call this basically f prime of x, right? And therefore, long story short, f prime of x is equal to, long story short, f prime of x, we define it as the limit of f of x plus h minus f of x divided by h as h tends to 0. This is the derivative of f of x this is the derivative of f of x, of course, at every point, and then you can input any point into any point. You will come up with a whole function for the derivative of the function, and that function gives you the instantaneous velocity at every point in the domain of the original function, right? So that's basically the idea of a limit. So basically, but now this is of course important, but then the idea of a limit is basically whenever you say that you're taking the limit of the function at some point, is that, for example, for whatever reason you cannot use the value of the function exactly at that point, so you get closer and closer to that point from the right and from the left, and then you note down the values of the function for all of those points and see what value basically the output of the function is tending to, and that's basically common limiting value is basically the value of the limit of the function at that point. So it's just, you're just getting closer and closer to that point in the domain of the function and noting down the outputs of the function, and then all of those values will be getting closer and closer and closer to some value, meaning that, for example, if I say that for example I have this function over here, suppose that I have this function over here, this is y and this is x. Now suppose that the function is even defined at x is equal to 0. If I say that the limit of f of x, and this is f of x is equal to x squared. If I say that the limit of f of x as x is equal to 0, that would be basically the same thing as the limit of x squared as x tends to 0. And as you can see, as you get closer and closer to x is equal to 0 from the right and left, the function is getting closer and closer to 0. So it's very simple to say that basically as you get closer and closer to 0 from the right and left, the values of the function are getting closer and closer to 0, meaning that the limit of this function as x tends to 0 is equal to 0. So it's just simply that simple idea that you need to understand, and that's the whole story. Okay, now that we understand basically the idea of a limit, the idea of a derivative, and the idea of I don't know, all of the other things that we talked about here, let's go to the next video, and then we will talk about the algebra of continuous functions. And see you in the next video, and thank you.